Now tell me, my screen is visible to you? Say yes or no.
Yes, sir. Visible.
Yes, sir.
Okay. So basic thing like it is invented by William Shockley in 1947, and it is a bipolar device that we discussed. Okay. So just I'm giving you an overview in 5 minutes, and then we will go for the numericals. So this bipolar junction transistor was developed by William Shockley in year 1947, and it is a bipolar device because here the current is carried by electrons and holes both. That's why it's called as the bipolar device. Or you, in other words, we can say because of majority and minority carriers. That's why it's called as the bipolar. Now, transistor means what? A transfer of resistance. Okay, that I will explain. This transfer of resistance, why we are calling as a transfer of resistance. That I will explain during the process, during when I will explain the procedure, how it's the current is flowing like that. Okay, so just for the starting, you understand transistor means transfer of resistance. That's why we are calling as a transistor. How? Because we have a three terminal, right? So here we are using for the input, and the other terminal we are taking as an output. One terminal is common. Input resistance and output resistance, if they are different, I'm not saying which is higher or which is lower. I'm saying if they are different, and it will be different in transistor, that's why it's called as the transfer of resistance. That means the input resistance, for example, is high and the output resistance is, for example, low. In that case, it's at, but whenever the carrier will move, it will be flow from higher resistance to lower resistance. Because of that, it's called as the transistor. Okay, and the third thing is what? Here we have a three terminals. One is what? Emitter, another one is base, another one is collector. And you know the construction of it, means which one is larger, which one is smaller. Okay, so tell me, highly doped terminal is what? Emitter, base, or collector? Out of this, which one is highly doped?
Emitter.
Emitter is, yes, emitter is highly doped, and collector is moderately doped, and base is lightly doped. And which one is having the larger area?
So collector.
Collector is a larger area. Now, first question is why? Why we need a transistor? Okay, so why we require the transistor? Suppose you are having the FM receiver, right? So whenever the signal is coming, it will be very weak due to disturbance because of traveling. Okay, like suppose you have a base station, okay, and the signal is coming like this in your home, okay, even in your mobile also. Signal is distorted by a lot of disturbance in between. So what will happen? You will receive very weak signal, and due to this weak signal, even you cannot get the correct one. So what you will do? You can amplify this signal. Whatever you are receiving here at the receiver end, you can amplify it. If you apply the amplification process, then you can receive some better signal. So this amplification is very important, and transistor can work as a amplifier. Transistor can work as a amplifier. That's why we require this transistors, because transistor can amplify the weak signal. Okay. Now, as I told you, we was having the three terminals, and to make is as a transistor, it should be of different material or different doping. So we have N-type semiconductor, we have P-type semiconductor, and we have a combination of three materials So either you can make NPN transistor or you can make PNP transistor. Okay. So either you can make this NPN transistors and PNP transistor. There is two possibilities only. Now how I will represent symbolically. So symbolically is like this one, where the center one will be the base, and this one is collector, and this is your emitter. If the current is coming out from the base to emitter, it is called as NPN transistor. This is the symbol for the NPN transistor. Similarly, for the PNP transistor, the current will go inside from the emitter. This is emitter, this is collector, this is a base. So this arrowhead is actually very important. So this is the symbol for PNP and that is the symbol for NPN. Now I can draw like this one. For example, this is a PNP transistor. Okay. And I'm assuming the base is common. For example, now this is what? Emitter, this is base, this is collector. Okay. As you can provide your input from this terminal, this is your input terminal and this is your output terminal. You can take output from here. Here you can see the base is common, as base is common in input as well as in output. This base, right? Base is common. If base is common, you can say this is common base. Common base. Now, the junction which created between emitter and base, you can call it as emitter base junction. And the junction which created between the base and collector, you can call as the base collector junction. As base is common for input and output or both the junction, you can call as this is emitter junction and this is what? A collector junction. Okay. Now, of course, we should provide some biasing. That biasing means what? Provide the external input for the operation. Now we will see the procedure and the operation of the circuit. So now I'm drawing same PNP junction, PNP transistor. This is PNP transistor, and in between them you will get a junctions. Of course, as we are having the two terminals, one is input terminal, another one is output terminal. I am drawing like this only. Here I'm taking input is forward biased and output is reverse bias. Why? That I will explain you some minutes. Okay, why we are taking the input as forward biased and the output as a reverse bias, that we will see in detail the procedure. Okay. Now, as this is forward bias, the P terminal will be connected to what? A positive of the input like this. And I'm assuming this output is a reverse bias. In that case, what will happen? P will be connected to the negative of the battery and the positive is connected like this. Right? Correct? Now you tell me, if it is positive and positive, what will happen? It will repel or attract. What will happen? Here we have a holes, right? These are the holes in the majority. So this is the positive. What it will do? It will repel, right? So it will repel, and the holes, as this is a forward bias, the junction width will reduce and the holes will try to jump in this region, in the base region. Okay. And as this is the emitter terminal, this current is called as the emitter current. Now what will happen, as some of the, actually this here holes are in the majority. Now holes are jumped into the base region, and as you know, base is lightly doped. That is the first thing, and its area is also very small. Okay, area is very small area. So there will be a very less recombination of holes with electrons because N is having the electrons, okay, as a majority. So what will happen when holes will jump into this base region? A small amount of holes and electrons will recombine and produce the base IB current. Okay, now again, this is reversed biased, right? So it will try to attract the, as this is negative, this is positive, or holes are there. So it will try to attract, right? It will try to attract, and these holes again jump here, and it will come and conduct, and it will produce the IC current. Always the current flow in the direction of holes. The current flow in the direction of holes, and opposite to the direction of opposite to opposite to the direction of electrons. So you can see as the holes are moving in this direction, right? So the current direction I'm showing in the same direction as the holes are moving, and IE is equals to IB plus IC. So from here also it's very clear that IE is equals to IB plus IC. Understand? Once again, I'm repeating the process. What is happening actually? This is forward bias, so it will repel the holes. Some of the holes will jump into the base, and as you know, the base region is having the very less width as well as very lightly doped. So electrons are also very less. So a small amount of holes will recombine with electrons, and it will generate IB, which is very small. Okay, small, and then that holes will again jump into the collector region and will produce the IC current. As IB is very small, and it is actually the combination of what? A collector current. So IE is equals to IB plus IC. Now similarly, you can see the procedure with NPN transistor. This is NPN transistor. I'm again doing the same thing, so I'm not explaining much here. This is your emitter, this is your base, this is your collector. Again, I want this one as forward bias and this one is reverse bias. That I will explain why we require this as a forward and this is reverse bias. Okay, and base is common. I'm taking this is common base. So what will happen? Again, I want forward bias, so negative will be connected to the negative of the battery, and like this. Okay, and this is reverse biased, and as this is reverse bias, N will be connected to positive, and like this. As this is negative, this will repel the electrons, right? And electrons will try to move in this direction, repel, right? A small amount of recombination will happen in the base region with holes, and electrons are moving in this direction. As the electrons are moving in this direction, the current direction will be opposite of the electron. So the IE will come out from here. Similarly, electrons are moving again because it's attracted by this positive terminal. So electron will come here, right? And the direction is like this. So again, you can see the collector current is just opposite of the flow of electron. So, and it's coming out from here. So it will be again IB is equals to IE is equals to IB plus IC. But of course, you can see the direction is opposite because here the majority carrier, in case of NPN transistor, majority carriers are electron. In case of PNP transistor, majority carrier, as you have seen, is holes. Okay. So we have seen the operation of NPN and PNP transistors. What are the advantages? There is lower power supplies, voltage is sufficient. That is some advantages. Okay. And now we will see why we are connecting like common base, common collector. Okay, so let's see the configuration. Configuration. That means there are three types, three terminals. Okay, we have a emitter, we have a base, we have a collector. So again, in the configuration, either you can take emitter as a common between input and output. You can take either base is common between input and output. Similarly, you can also take collector as a common for input and output. Let's start with common base. Common base. In common base configuration, that means base is common, right? And for the NPN transistor, you can draw like this. NPN means the current will come out. This is NPN, NPN transistor, because the current is coming out and from the emitter only. Okay, and the direction of current you have to show from the emitter terminal only. This is collector, and as the base is common, this is your base. So now here, as you know, you can apply the inputs here, and I'm assuming this is what a forward bias, because emitter base junction is what input terminal. So this is forward biased, and this is N terminal, this is P, and this is N. So N will be connected to a negative and then positive like this. Similarly, you can connect N to the positive and then to negative. Of course, we require some input and output resistance. You can also draw here RC value. This is the collector resistance, right? And as this is a reverse bias, of course, you will get some higher value of RC because it's a reverse bias. Okay, now here you can amplify the signal. So what will be the current amplification factor? Now you see. First, you see what is the input current. The direction I already explained. It's opposite of the electron flow. So I is coming out like this. IB is coming like this, and IC is going like this. This is a collector base voltage. It's a collector and base voltage, and this you can assume this is VEB. That is the emitter base voltage, VEB. Right. So here in this case, as you know, this is forward biased, right? So here the ratio of this is called as the current amplification factor. Current amplification factor in case of common base configuration. Current amplification factor has come into existence. That is alpha. Alpha is nothing but the ratio of the change of current IC by the change of current IE. What is that? The change in the output current. This is your output current, right? This is your output current and this is your input current. As you are doing the amplification, you have to check how much output you are getting and how much input you got, right? So so the ratio, if I'm saying what is the efficiency, how you will calculate it? By taking the output by input, right? Like if I'm judging any student, how I will check how much how many questions I gave, like 100 marks question, and he's securing 25, 30 marks. So like that, we can check its amplification factor, right? So similarly here, you have to check with output by input. So as you can see, in our case, we have an output of IC current, and we have a input as IE current. Now, if I see this is the collector current, okay, collector current, and collector current is equals to what? Collector IC is equals to alpha IE. But problem is what? It's a reverse biased. This is a reverse biased. And in in the reverse bias, what is happening? The current will flow because of minority carrier. Okay, as this is the reverse bias, right? This is a reverse bias, and in the case of reverse bias, as you have seen, because of high width of the depletion region, only the minority carrier current will flow, and that is actually the leakage current. So here there is some leakage current also flow. So if the emitter base voltage, that is VEB, is 0, even then the flow, so you can write down here when VEB is 0, even if VEB is 0, even then there is a flow of a small leakage current. And it is called as the base current with output open. So that's why it's called as ICBO. Alpha IE is equals to IC. So this is the formula. That means this is the flow of current between collector to base when emitter is open. Okay, when emitter, that means input, we are not providing any input, even though there is a leakage current because of this reverse bias. Once again, you see when I'm drawing like this, okay, this is one terminal and I'm saying input is open circuited, but because we have a two terminals and the second terminal is reverse bias. Because of this reverse bias, the current flow because of minority current, that is called as the leakage current, right? So here what will happen, there is some leakage current flow even when your input voltage, that is VEB, is equals to 0. In that case also you are getting some leakage current, and that leakage current is called as the current between the collector, this is collector and this is the base. So this is called as the current between collector and base when emitter is open. Collector and base when emitter is open. Okay, so that's why is IC value, IC is equals to alpha IE plus ICBO. And as we know that the IE value is equals to IC plus IB. So please substitute here in this equation. Okay, so if you substitute it here, what you will get, IC is equals to alpha. In bracket, you can write down IC plus IB plus ICBO. What is that? The current between the collector and base and emitter is open. Okay, now you can see IC 1 minus alpha is equals to alpha IB plus ICBO. And then you can find out the value of IC is equals to alpha divided by 1 minus alpha IB plus ICBO divided by 1 minus alpha. I just solved further. That is numerically I solved it. So this is what the collector current when alpha is given to us, then we can find out the value of IC. If you know the value of IB and you know the value of ICBO, you can find out its value. Okay. Now we will see what this was the common base, right? We started with common base. Now we will see the common emitter. So this is common emitter. As the name indicates, the emitter is common between. So what you can do, you can draw like this, and I'm showing the current direction here. Okay, and like this. So here, this is a collector, this is the base, and this is the emitter junction, right? And I am assuming that the emitter is common. That means emitter is common for input as well as for output. As I told you, you have to take the output as a reverse bias. So of course, there will be some resistance, and you can apply here the negative to positive if you are taking as PNP transistor. This is PNP transistor. So P will be connected to negative, and you can assume this is VCE. Similarly, this is N, so N will be connected to negative, and this is positive. And you can assume this is what VBE, right? And emitter is common for the input as well as for output. Now, as you can see here, the current IB is coming. Okay, IB, sorry, here the direction will be because of the holes. Okay, so the current is coming like this. This is IB, and this is IE, and this is IC. You can check with the flow of electrons and holes how the current is moving. Okay, Now you tell me what will be the input as we have seen the amplification factor. Amplification factor. Amplification factor is what? Output by input. So output, and in the common emitter case, amplification factor is given by beta. Beta is equals to the output current, that is IC, change in IC divided by the input current. Input current is what? IB. So it's a IB. That's why beta is equals to IC by IB. Right? And you know, we have seen alpha. Alpha is what? IC by IE. These two formulas are important. And other thing is what? IE is equals to IB plus IC. Now you can find out the value of IB from here. What is that? IB from this equation. IB is equals to IE minus IC. You can substitute it here and tell me the value of beta. Beta is equals to you see IC by IB. In place of IB, I can write down IE minus IC. So if you solve it further, and you can also do one thing here, you can write down you divide it by IE. So IC divided by IE, 1 minus IC by IE. And you know, IC by IE is what? Alpha. So you can also write down beta is equals to alpha divided by 1 minus. Okay, so that is the second formula. Now you see, in the previous case, we calculated the value of IC. Here also you have to find out the value of IC. IC is equals to alpha IE, right? But second thing you see, here we are not providing any input, right? We are not providing any input. So this leakage current will be equal to what? ICBO. Right? So now that you know, right? That is alpha, alpha IE. This is alpha IP plus ICBO. That I am writing from the equation from common base. Okay, and this IE, sorry, IC is equals to alpha. Yes. So IE, we know that IE is equals to what? IB plus IC. If you substitute it here, what you will get? IC is equals to, we have already calculated, so I'm directly writing 1 minus alpha IB plus 1 ICBO divided by 1 minus alpha. That is the equation that we got from the first common base configuration. But you can see here we are not providing the input, that means base is open. So in the case of common emitter, you will get the leakage current as ICEO. Why? Because base is open, base is input. Okay, as I told you that you will get the leakage current. This is suppose NPN transistor, right? This is any transistor, and I'm saying, oh sorry, like this you have to make it. So this is a base and this is the emitter. For example, this is the base and this is the collector. I'm saying I'm not providing any input, even though you are getting some current because of the reverse bias. Okay, that means base is open. In this case, base is open. So that's why it's called as ICEO. That means the current between collector and emitter when base is open. That's why it's called as ICEO. That means the value of ICEO is this one. So the value of ICEO will be equal to ICBO divided by 1 minus L. So ICEO will be equal to 1 divided by, ICBO divided by 1 minus L. So if you know the collector to base, if it is open, what is the current? You can find out its value of ICO by this formula. So this is the again and next important formula for us. So that was the common emitter. You can also see for the common collector. Common collector. Common collector means what? Again, as you know, collector will be common between input and output. So I'm drawing like this only. I'm showing the direction of current from this terminal.
Can you scroll up for a minute?
Yes.
Can you explain that part again? That IC, how
Yes,
you
yes.
got the final equation?
See, this is the equation of a IC current in the common base, right? That you calculated. You can see here. This is the common, IC value when you are having a common base. Is it clear? Say yes or no?
Yes, sir. Yes, sir.
Okay. Now, as I told you, we was having the ICBO current, when I am assuming that leakage current means what? Leakage current. First, I explain you leakage current. Okay, leakage current. Leakage current means what? When any terminal is open circuit. If it suppose like this, if any terminal is open circuited, okay, there is up here this was a reverse bias, right? In the reverse bias, the width will rise because of reverse bias, the width will rise. And in this case, in the case of reverse bias, current will flow only because of minority carrier. In case of forward bias, the current will flow because of majority carrier. So the current which will flow because of minority carrier is called as the leakage current. That is the first thing, leakage current. And what if your input terminal is open circuit? That means we are not providing any input from the input terminal. Okay, when this is input, even though there is some current will flow because of these minority carriers. Because of this minority carrier, some leakage current will flow, and which will be what? As this is what a base is common. For example, this is emitter, this is collector, right? So the current which will flow because of this minority carrier is equal to ICE, ICBO when emitter is open. Emitter is what? ICBO. Emitter is input, right? So its meaning is simple. When your input terminal is open, whatever the leakage current, it will be denoted as a collector to base current when your input, that is emitter, is open circuit. That was the case with a common base. Now if I see for the common emitter, right? So here what is happening, you see, this is emitter and this is a base, this is the collector. Now I am saying input is a open circuit, right? This is open circuit, open. And the current which flow between the emitter to collector to emitter when your base is open circuit. This current is again a leakage current only because of minority carrier. So it's a leakage current in common emitter, same thing. So in the equation, this is a leakage current, right? So whatever we discussed, see, in the common base, this one is what? A leakage current. Leakage current, right? So in this case, this is what? This is equal to a leakage current of common emitter. So that's why this total equation is equal to ICEO. Understand? Is it clear?
Yes, sir.
Okay, now we will see in the common collector, as you know, here the collector will be common. So I am drawing like this because I can draw at least. This is input and this is your base, this is your collector, and as you can see, the collector is common for input and output. This is a common collector case, right? And again, you can make the resistance and you can make it reverse bias, and this is forward bias, right? So you know, this is if you are drawing like NPN transistor, PN transistor. So this N will be connected to positive, negative like this, and this is positive, so positive, negative. That you know, right? how to connect a forward and reverse bias. Now you tell me what will be the input current will be IB and the output current will be IE, right? Sorry, IE. So the current amplification factor, because of the configuration, current amplification is given by gamma, which is equals to output current, that is IE, divided by the input current, that is IB, and this is the change, right? So the gamma is equals to IE divided by IB. Is it okay? Now, as we know that alpha is equals to IC plus divided by IE from the common base configuration. And also we know that the current, that is emitter current, will be sum of IB plus IC. You can substitute its value. So in this equation, if I substitute, the gamma is equals to IE divide by, in place of IB, I can write down IB is equals to IE minus IC. So it will be IE minus IC, right? And also you can do like this, divide it. So IE divide by IE divide by IE divide by IE minus IC divided by IE. That means I've just divided both numerator and denominator by IE. So you will get 1 divided by 1 minus alpha. Why? Because this IC by IE is alpha. Okay. Now the next thing is what? The collector current, as we know from the common base, it is equals to IC alpha IE plus ICBO. Right? And IE is equals to IB plus IC. That also we know. So we are substituting the value of IC from here to here. So what you will get? IE is equals to IB plus, in place of IC, I can write down alpha IE plus ICBO. Okay, so from here I can just simplify the expression. 1 minus alpha is equals to IB plus ICBO. So this IE will be equals to IB divided by 1 minus alpha plus ICBO divided by 1 minus alpha. And this 1 minus alpha, 1 divided by 1 minus alpha is equals to beta plus 1. Okay, so you can substitute it here, and that will be equals to IE equals IE is equals to IB multiplied by B plus 1 plus beta plus 1 ICBO. In the previous case also we saw that it was a leakage current, right? So it's again a leakage current. So that was the formula that we required for it, right? These are the formulas that we have seen. Now we will do one thing. We will solve some numerical based on it, and that will give us a clear idea what is actually there. Okay, so let's start with some numerical. Question 1.
You show the formula.
What happened?
I said this formula.
So I'm giving the question like we have a common base transistor which has a input resistance. I'm talking about common base CB. Input resistance, they have given input resistance. Suppose it's 20 ohm. And they are giving output resistance is equals to 100 kilo ohm. Why? Because this is forward biased, so the resistance is very less, and this is reverse biased, so the resistance is very high. Now they say that the collector load, RC, you can say collector load is 1 kilo ohm. if the signal, that means input signal they are giving, is 500 millivolt, they're saying V in is 500 millivolt is applied between emitter and base or VEB. So both are same thing. Either you can assume this is input or this is VEB. They are saying find out the voltage amplification. Find voltage amplification. Amplification, and they say that I'll assume alpha is equals to 1. Write down this question. They say that you have a common base configuration. Input resistance is 20 ohm, output resistance is 100 kilo ohm, and RC, that is the input, collector resistance is 1 kilo ohm. Input voltage they are giving like 500 millivolt, and they said that alpha is equals to 1. So again, I'm drawing the same thing here, what they actually given us. Okay, here they are saying this is emitter, this is base, this is collector. Okay, and here assume this input as 500 millivolt. This is the IE. They said that the input Rn is 20 ohms. And this is the IB current. And this is the RC, that is the collector resistance, which is 1 kilo ohm. And IC is coming like this. And they said that the output R out or output resistance is 100 kilo ohm. Okay, so what will be the first step for us? Find out the value of IE always, right? Because you know the current amplification, this is the common base configuration. So alpha will be what? Alpha will be equals to, if okay, I will explain.
Sir,
Yes,
sir, in question it is not given that RC is 1 kilo ohm, right?
RC is 1 kilo ohm.
Oh, sorry, sir, I didn't see that.
What?
Sorry, sir, I didn't see that.
Okay, okay. So RC is given to us, right? Now, what will be the first step? See, Rn is given to us, that is the input resistance. We know the input voltage. So can we find out the IE? IE is equals to Rn divided by the V in, oh sorry, V in divided by Rn. V in divided by Rn, right? So this is 500 millivolts and Rn is what? Or 20 ohm, which will be equals to what? It's a 25 millivolts, right? This is what IE. They said that alpha is equals to 1. So if alpha is equals to 1 and
So
alpha,
milliampere. 25 milliampere.
milliamp, yes, milliampere. They said that alpha is equals to 1, right? So if alpha is equal, and what is the formula for this one? Output by input, right? And it is equals to 1. So, and we know the value of IE. So can you tell me the value of IC?
25 milliamp.
25 milliampere.
It will be same as that of 25 milliamps, right? So now we have IE, we have IC. We have to find out the voltage amplification. Voltage amplification means what? We have to find out AV is equals to V out divided by V in, right? This is called as the voltage amplification. Voltage amplification. So we have IC. We don't know what is V out, right? So for V out, how we will calculate? V out will be calculated in this terminal across the RC. So we know the RC, we know the IC. Can you tell me the V out? From here only we can tell V out is equals to IC into RC, right? So here V out is equals to, yes?
So we have to add R out with RC, sir.
No. Load. See, you if you got the value of IC, it will be coming here. We have to find out across the RC. Whatever the across the RC, that will be your output. This is actually your load.
Okay, sir, got it.
Okay. So V out will be equals to IC into RC, which is equals to 25 milliamps, and RC is given to us is 1 kilo ohm. So that will be equals to 25 volt. And we have to find out the voltage amplification. AV is equals to V out is what? 25 divided by V in. What is the V in? V in was 500. Yes.
500.
So what will be the answer?
50
sir.
volt.
50 volts. 50, sir.
50 only because amplification. So it does not have any units. Okay, now second question. I'm talking about common base. IE is given to us 1 milliamps. IC is given to us 0.95 milliamps. Find out the value of IB. First, everyone try by your own and tell me the answer.
$0.05
Yes, because it is equals to IE equals to IB plus IC, and if you substitute all these values, you will get IB is equals to 0.05 milliamps. So the today's last question. Question number 3. I'm talking about common base connection only, and the alpha is given to, because in the common base we have alpha, right? Alpha is equals to what? Output IC divided by IE, and which is given to us is 0.9. They said that IE is equals to 1 milliampere. Determine the value of IB. Try by your own.
milliamps.
Yes, correct. So IC is equals to alpha IE. From there you can get the value of 0.9 milliamps. And if you substitute it here, you will get IB is equals to IE minus IC, and by that you will get 0.1 milliamps. Okay, so we will solve some more questions based on the BJT, and also we will start MOSFET in the next lecture. So that's all from my side. If you have any doubt, you can ask. I will take your attendance directly from Microsoft Team. That's all.
Thank you, sir.
Sir,
Yes.
sir, for CAT 2 we'll have module 3, module 4, or
Yes.
will there be 5 also?
That I will check and then tell you. I will check the guideline and then I will.
Okay.
Can you share today's PPT?
Yes, sure.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
I'm sharing the PPT. Please download and then leave.
Thank you, sir.
Thank you. So I shared the PPT, today's PPT. Please download and then leave. Thank you.